right, so 6.3, we're going to do binomial and geometric distributions here. And we're going to see when to know when something is binomial or geometric, and then find the probabilities when they are. Yay! So a binomial setting, in order for something to be binomial, it has to check out with all four of these conditions, and a little mnemonic device is kind of doing your bins. So in order for it to be binomial, you have to know, is it binary, meaning two things, right? Is it a success or a failure? If you have two different outcomes that can occur, success or failure, then that means it's binary. So is it independent? So one trial cannot affect any other trial. Okay. So drawing cards, you'd have to replace them. If you didn't replace them, then it would be dependent. And then is there a fixed number of trials? So we have a fixed number of trials going on. And is the probability for success the same for each trial? So the same success, okay? So if you want to kind of remember to check your bins, you always have to show these four things before you can say, yes, this is a binomial setting, and I'm going to apply what I know for binomial distributions. All right. So just a little definition. The count x of successes in a binomial setting is a binomial random variable. The probability distribution of x is a binomial distribution with parameters n and p, where n is the number of trials of the chance process and p is the probability of success from any one trial. Now remember, probabilities are between 0 and 1. The possible values for x are going to be whole numbers from 0 to n. And this is really important, so you could say 0, 1, 2, 3, 4, all the way up to however many you're dealing with. So when I have this going on, it's good to know that this would be kind of discrete values. So there's just 0 to 1. Okay, it's not everything in between. Okay. So let's determine first off whether these random variables are binomial. So we're going to have to check for our bins. So number one would be rolling a fair die 10 times, and x is going to be the number of sixes. All right, so is it binary? Yes, you either get a 6 or you don't. Is it independent? Yep. Rolling one die doesn't affect the next roll. Do you have a fixed number of trials? Yes, it told us that we're going to do this 10 times. And is the probability for success always the same? Yes, the probability of getting a 6 on rolling a die would be 1 out of the total of 6. So the probability is always a 1/6. All right, try this next one. Shoot a basketball 20 times from various distances on the court, and y is the number of shots made. So think through, checking all of those. You can pause. And let's see. Is it binary? Yes, you either make it or you don't. Is it independent? And this can be questionable, but yeah, it's reasonable to assume like that one shot's not going to affect the next. However, if you're like on fire that day, like it could just keep affecting, but for the most part it is independent. Okay. The number, is there a fixed number of trials? Yep, told us we're going to do this 20 times. And success is the same. Is the probability for success the same? Well, I would say no. Think about if you're on this basketball court, right? Here's a basket and here's a basket, and you shot from right here. Well, there's probably a high success rate that you're going to make it. But let's say you tried to shoot the ball from way out here, then it's probably a much lower success rate. And that's why they always make you on those competitions, like it's a hard shot to make for the $1 million, right? Okay, so no. Observe the next 100 cars that go by and C is the color. So is it binary? Nope, there are more than just 2 colors of cars. So this is not going to be binary. And C is not even a random variable since outcomes aren't numerical. So we can stop this. We don't even have to check anymore. This would not meet the condition. All right, so if you want more, see if you can do these next 3. Otherwise, if you feel good, you can keep going. And the answers I got were yes, no, and no. And 2 would be no because it's not independent. And 3 would be no because the probability of success changes. So if you replaced everybody going on, then you could have independence, okay? Okay, so let's look at this family about being able to have kids going on. Each child of a particular pair of parents has a probability of 0.25 of having type O blood. Genetics say that children receive genes from each of their parents independently. If these parents have 5 children, the count X of children with type O blood is a binomial random variable with n equals 5 trials, and the probability P equals 0.25 of the success on each trial. In this setting, a child with type O blood is a success. And a child with another blood type, we're going to say, is a failure. So I want to know what's the probability of having 2 successes. So that means we could do success, success, fail, fail, fail. All right. Well, could we also do that in a different arrangements? We could go success, fail, success, fail, fail. We could do success, fail, fail, success, fail. We could do success, fail, 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 success. And there's a few more ways, but you get the idea. How many different ways could we arrange the way that we're going to do this? And you could keep going and see how many different arrangements there would be. Oops, keep going. That's weird. Okay, so here you can see that there are 10 arrangements if you kind of kept that up. So now it says verify that in each arrangement, see what happens, that you get your probability of 2. So let's see. We'd have in each arrangement 0.25 for success times 0.75 for failures. So you'd have 0.25 times 0.25 times 0.75 times 0.75 times 0.75. So in all of those, you're going to have 0.25 twice and 0.75 3 times. So for each one of those, it is 0.02637. But I had them 10 different ways that I could do those combinations. So I'm going to take that and multiply by 10, or you could add them all up, which is the same as multiplying by 10. And you can see that the probability is 0.2637. So about a 26% chance that exactly 2 have success. Okay, so in the previous example, any one arrangement of 2 successes and 3 failures had the same probability. This is true because of the way that we showed of the multiplication. Multiplication is commutative there. All right, so in general, we can say that P, where exactly K successes and N trials, we could say the number of arrangements times the probability of success raised to the K number of trials, or K number of successes, times the probability of failure, because 1 minus the success would be the probability of failure. So the probability of failure equals 1 minus the probability of success, raised to the total number minus however many we had for successes. So that would give us the total overall. There's another way that you could do this in the calculator. You could have N choose K here going on. which the formal formula is n factorial over k factorial times n minus k factorial. Just a little review of factorial. If I had 5 factorial, that means I take 5 times 4 times 3 times 2 times 1. So I do all the integers starting at 5 down to 1 and multiply them. So 9 factorial would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. All right? Okay, so in your calculator, you can go to the math, over to probability, and do n choose r. So if I wanted to do the 5 choose 2, I would type 5 and then go math, probability, n choose r, and then type in the 2, and it tells me that that gives me a 10. And that's what we found. We said, hey, if there's 5 things going on with 2 successes, how many different ways can I arrange them? Well, 10 times. That's what we just did. Or you can do it by hand by using your other formula. So you're going to have 5 factorial over 2 factorial times 3 factorial. So let's see, those cancel. 2 will cancel here, and you're left with 10. Okay? Okay, so the binomial probability here, for those of you who like to show everything out by hand, I'm going to show you in your calculator what you can do as well, are you're going to have your n choose k going on, so the number of arrangements with k successes, times the probability of success with the number of successes that you have, times the probability of failure with the number of failures that you have. And this is on your AP formula sheet that you get to use on everything. Okay, you can also do this in your calculator, which is really nice. However, if you use calculator speak, you have to explain everything that's going on. I don't know how many times I'm going to tell you that. Otherwise, you can always set it up by hand. Personally, I like to do the calculator. So, go second distribution on your calculator. Let me get mine out so I can tell you exactly where that's located a little bit. All right. I'm sure you're getting your calculators out too. So second distribution, when you have your home, like the screen, and then you have the buttons, and then you have those guys right here with the ups and downs, there's vars, and it's right above that. So you got to do second vars or second distribution. And then you can toggle up or down. I'm going to go up. I think it's faster to get to the binomial PDF and CDFs. So if you toggle up or down, hopefully you can see these guys right here. That's what we're going to be using. A binomial PDF is the probability for just one value. So that's when you have like x equals k. So when I want just 2 successes, that's when I'm going to do a PDF. If I said what about 2 or less, then that's going to accumulate lots of things. And I think C is for accumulating. So here, if I wanted like the 0, the 1, and the 2, if x is less than or equal to 2, then I can compute the CDF in my calculator. NPK, N is the number of trials. P would be the probability of success. And K is the number of successes. And that's where you're kind of picking it from there when it says x equals k. And I always remember like PK for the formula. I don't know if any of you guys have ever danced or seen dancers, but you have to make PKs when you're twirling, if you can envision me twirling right now, or not. Okay, so NPK is how I remember. The N is the number, and then you go PK, PK. Okay, so again, if you are using this calculator feature, you must write out what everything means. Tell me what you're doing on the test for me and on the AP exam, or you will not get any credit for your calculator talk. All right. crap, this one already had it up, sorry. Each child of a particular pair of parents has a probability of 0.2 of having type O. Suppose that the parents have exactly 5 children. So now, what if I wanted to do the probability that exactly 3 children have type O instead of the 2? So now I'm going to say I'm going to do in, so 5 choose 3. So 5 combinations with 3 different ways that I could get a success, times the probability of success, which is 0.25, times the probability of failure, which is 1 minus 0.25 or 0.75. And then you can put that in your calculator if you want, or you could do the formula of the choose R, or R choose N and choose R. Oh my god, I just forgot. Let me go math probability and choose R. Sorry. So go to that and choose R and do 5 and the 3, and you should get out 10. And then you can multiply everything out, and that is the probability of exactly 3 children having type O blood. So then it says, should the parents be surprised if more than 3 of their children have type O blood? So the probability of more than 3 is set up like this. So more than 3, you could do this a couple ways. You could do 1 minus the probability that x is less than or equal to 2. Now we don't want to say, less than or equal to 3. Okay. Less than or equal to 3. So the probability of getting a 1, a 2, or a 3. Or I could say I want to find the probability that x is equal to 4 plus the probability that x is equal to 5, because that's the most that they could have is the 5 children. So you could do either one of these 2 ways. If you did it this first way, you're going to be using that cumulative binomial one. And if you're doing it the second way, then you're just going to use the PDF going on for the binomial. Okay. Now, why can't you say x is greater than 3? We don't have a feature in our calculator to do that, so that's not going to work. That's why you need to convert it back to this. And remember, the only possibilities for success are 0, 1, 2, 3, 4, and 5. So if I want greater than 3, I'm only looking at the 4 and the 5. Okay. So if I did it the first way, like we said, we could do 1 minus the binomial CDF, because we're accumulating all the way up to the 3. So we have our number, which was 5 kids, probability of success, and how many we wanted to accumulate up to. So this would mean 0, 1, 2, and 3. So that's option 1. Or we could have done, I don't know if I have it on here. Yes, I do. We could have done the probability of x plus 4. Or sorry, the probability of x plus the probability of being 4 plus the probability that x is 5. And here, this is all out by hand, or you could have done this in the calculator as well. So this would be the binomial PDF of 5, 0.25, 4, plus the binomial PDF of 5, 0.25, 5. Either way you do this, the answer you should get is 0.01563. Okay. So, let's read this a little bit now. We got to answer the question. Should the parents be surprised if more than 3 of their children have type O blood? So if more than 3 of them, gosh, the probability was only like a 1.5, 1.6% chance. So I would be really surprised if they got that, because that's a really, really small chance. Okay, so a little common error when using the complement rule, what we kind of talked about. So make sure that you know if you want the probability of finding more than 2, okay, more than or equal to 2, it is not going to be 1 minus x is less than or equal to 2. Because think like when we had the kids, for instance, 1, 2, 3, 4, or 5. So then if I wanted more than or equal to 2, I would want to find those. So the complement would just be the 0 and 1. Okay, so if you said 1 minus less than 2 right here, then I'd have to basically, when I put it in my calculator, I'd need to put a 1 in there, because if I put a 2, it's going to include it in that binomial CDF. All right, hopefully that makes sense. If you need more help, let me know. This is a really common mistake, though. Make sure that you have this down. All right, so rolling doubles. When rolling doubles, okay, so when rolling 2 dice, the probability of rolling doubles is 1/6. And you can figure that out if you wanted to. Suppose that a gamer rolls the dice 4 times, hoping to roll all doubles. Find the probability that the player gets doubles twice in 4 attempts. So I'm going to let you think through what you would do. So is this a binomial setting? Can we even use a binomial PDF or CDF on this? So let's see, is it binary? Yep, we either get them or we don't. Doubles or no doubles. Is it independent? Yes, so one roll doesn't affect the next roll of rolling the 2 die. Is there a fixed number? Yes, it told us that it would be 4 times. And is probability for success always the same? Yes, because they told me that that's 1/6, and we could also find that. Okay, so we can do a binomial PDF or CDF on this. So it says find the probability that the player gets doubles twice. So we are looking for the probability that they get doubles twice, and only twice in the 4 attempts. So here I could do the binomial PDF. Let's see. There are 4 attempts. The chance is 1/6. And I get out, I want to find 2 successes. So you can put that in your calculator. And you should get approximately 0.1157. So part B says, should the player be surprised if she gets doubles more than twice in 4 attempts? Well, let's see what that probability would be, and then we can tell her if she should be surprised or not. So I'm looking the probability of more than twice. So let's think about that complement rule. If it's just more than twice, then I'm going to do 1 minus the probability. So more than twice out of the 4. So I have 0, 1, 2, 3, and 4. So more than twice is 3, 4. So the complement would be 2 or less in this case. This is going to be a cumulative. So I have 4 attempts. Probability of success is 1/6, and I want 2 or less. So that is approximately 0.0162. Make sure you can get that. So yeah, I'd be a little surprised because that's not a very high probability, less than 2% of a chance. Okay, to introduce my class to binomial distributions, I give a 10-item multiple choice quiz. The catch is students must simply guess an answer, A through E. So I just give you a 10, and you just guess A through E, and you don't really even know what the questions are. So then I use my calculator. I'm going to do a random number generator to produce the answer key. Y'all know I like to do random number generators. All right, so Brett is one of our students in this class, and X is going to be the number of Brett's correct guesses. So now show that X is a binomial random variable. So before I even begin, I need to make sure I do that. So, is it binary? So yes, you either get it right or you get it wrong. Is this independent? Yes, since I did a random number generator, it will be independent. Is there a fixed number? Yep, I said I'm going to give a 10-item quiz. And is the probability for success always the same? Yep, because you can get 1 out of 5 right each time, because you're just guessing. So the probability of getting it right would be 1 out of all of the probabilities A through E, which are 5. Okay, so let's look at the next question. Find the probability that x is equal to 3 and explain what this result means. Alright, so I'm going to do, if it's just 3, a binomial PDF. The number of times I'm doing it is 10. Probability for success is 1/5. And I want to know that I get out 3 successes. And I get approximately 0.2013. So this tells me the probability of getting 3 correct would be 20%. So the probability that Brett gets exactly 3 correct is about 20%. Alright, so to get a passing score on the quiz, that'd be a 60%. A student must guess at least 6 correct times. So would you be surprised if Brett earned a passing score? Well, let's see. What would be the probability of at least 6 times? So I could get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 right. So at least 6 would be 6 or more. So here, if I want to find, using my complement rule, a passing score, I do 1 minus the binomial. I'm going to do accumulating CDF. The number of times is 10. The probability of success is 1/5. And I'm going to do it for 5 or lower. And then subtract again that probability from the 1 to get 6 or more. Alright, so I got 0.64% chance that they would pass. So whenever I have a student that I ask, hey, how'd you get these answers? You know, you got a C on this test. How did you do all of this? And they're like, oh, I don't know. I just guessed. I can be like, oh, yeah? I don't think you did because that chance is really small. So we can support that with probability. Woo! Gotta love it. Okay. Mean and standard deviation of a binomial distribution. Okay, so we still want to describe by looking at the shape, the center of the spread, any outliers, the variability, all of that fun stuff. So here, consider the probability distribution where X is the number of children with type O blood in a family with the 5 children. And here are all the probabilities of having 0 with the type, 1 with the type, 2, 3, 4, and 5 with the type. And here's the nice little probability distribution. So if I wanted to describe the shape, I could see that that is skewed right. So it's more likely to have 2 or less kids that have the type O blood. Here I can describe the center by the median, okay? Because since it's skewed, you'd like to do the median. If you wanted to try to find the mean, you definitely can. You can take 0, that expected value formula, 0 times the probability of 0 plus 1 times the probability of 1, etc. But definitely use the median since the data is skewed. So let's see, where would the median fall in there? In here. Okay. And let's see. The spread. So the spread, you could find the interquartile range So if you put all that into that one variable statistics, if you wanted to talk about the variance, then you could find the variance by doing the one variable statistics as well, or putting that all in your calculator. I'm going to go ahead and put in my list really quick. So stat edit, just so I can state what those are. I don't think I got them typed up. So 0, 1, 2, 3, 4, 5, 0.23, 3.39, 55.2637. Hopefully you're putting it in your calculator too, so you can look 0.0147. Make sure I don't have a typo. 0.00098. I'm just going to look, make sure I have them all in there correctly, and go stat, calc, one variable stats, list 1, comma, list 2. So I got a mean of about approximately 1.25, and my standard deviation was approximately that. Here I saw my median was 1, which is where we definitely thought it would fall in. My interquartile range, let's see, my interquartile range would be 1. So if I did Q3 minus Q1, that would be 2 minus 1, which is 1. Okay? And that's, I would describe it with the IQR, but you could still find the variance. Sorry, this was the variance. The standard deviation, I'm just kind of double checking, the standard deviation was 0.96845, if you wanted to have that. Okay. Oh, there I showed it typed up, but all right. So that's what we were just talking about, putting them into the list, and that's easier to find. But with the skew, I would check for the median and the IQR. Okay. All right, mean and standard deviation of a binomial distribution, and you can find these on your formula sheet. So your mean is just the number times the probability. And your standard deviation is the number times the probability of success times the probability of failure square rooted. And again, these are on your formula sheet. If you go to your formula sheet under binomial, you can see these two. So it's nice and easy to keep track of. So let's do this one. My 21 AP Statistics students did a bottled water versus tap water activity. And this is basically like I just gave them some bottled water and tap water and tried to see if they could tell which was which is funny because usually you can't. Anyway, if we assume the students in our class cannot tell tap water from bottled water, which is actually pretty true, then each has a 1/3 chance of correctly identifying the type of water by guessing. So I gave them 1 bottled and 2 taps. Okay? Okay, let X equal the number of students who correctly identify the cup containing the different type of water. And it wants me to find the mean and the standard deviation of X. Well, this would be a binomial distribution. We can go through that. Probability of success is guessing right. Probability of failure is not. Independent, one guess doesn't affect the next person's guess. You all are independent individuals. There's a fixed number. Okay, I have 21. And the probability for success is always the same. It'd be 1 out of 3. All right, so we're going to use our formulas for this. I know that my formula for the mean is n times p. Well, n is 21, p is 1/3, so the mean, the expected value, would be 7. So we'd expect about 1/3 of the 21 students, which is about 7, to guess correctly. The standard deviation is the number 21 times the probability of success, 1/3, times the probability of failure, which is 1 minus 1/3, or 2/3, and square root all of that and get 2.16. So if the activity were repeated many times with groups of 21 students who were just guessing, the number of correct identifications would differ from 7 by an average of 2.16. You could also use that 68% rule that we've talked about. Okay, let's see how you do in this guy. And you can pause, and I'm going to go ahead and get the answers up for you. And hopefully you did okay. If you have any questions, let me know. All right, so we're going to go to this next one. Binomial distributions and statistical sampling. So the binomial distributions are important in statistics when we want to make inferences about the proportion P of students in a population. So we're going to take this sample and see if we can't infer things about the population. Suppose 10% of CDs have defective copy protection schemes that can harm computers. A music distributor inspects a simple random sample of 10 CDs from a shipment of 10,000. Let X equal the number of defective CDs. What's the probability that X equals 0? All right, so here the actual probability of no defectives would equal this. So we could use our probability distribution to pretty much approximate it though. So we're not finding the actual. That would take us a lot of time writing all of those in. So let's say I wanted to approximate with the binomial. So I could say 10 choose 0 times the probability of success, or sorry, well, I guess the probability that it's not defective, right? Or what did it say? 10% of the students have defective, so the probability of defective, and then times the probability that it's not. Okay, so 10% it told us, and then so 1 minus 10% would be 0.9. And we approximate it to be 0.3487. So we're really close, very, 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 very close to the actual probability. So this will give us a good approximation using this binomial distribution. And you could have done this in the calculator just as well using the formula, the binomial PDF, just to review, of 10.100. All right. So the only thing in order to use this binomial distribution is we have to make sure that we're independent, or that we have at least more than 10% of the population. And I'll call this the 10% rule a lot. So this says that 1/10 of the population, our sample has to be smaller than the 1/10. Okay, so we need no more than. So no more than, if you want to kind of put, no more than 10% of the population. Okay, so I always kind of adapt this, and I do 10 times however number in my sample, and I say, would that be smaller than the population? Okay, and that's how I look at this rule. I take 10 times the number of data that I have. Number of data would make more sense. And then I see if that's smaller than the population. Okay. So as n gets really big, something interesting happens to the shape of a binomial distribution. What do you think it is? Hopefully you can see as n gets bigger and bigger and bigger, binomial distributions will become more and more normal. So that's what we're looking to try to approximate that normal distribution with a binomial distribution. So as n increases, the shape gets to be more and more normal. All right, the normal approximation for binomial distributions. So we already knew our standard deviation and our mean. And the other thing we have to check now is that we have at least 10 successes and at least 10 failures for that sample to be big enough to approximate normality as well. Okay, so I would take n times p, and I want to say that that's greater than 10. That's basically saying I have 10 successes going on in all of my attempts, and I have 10 failures going on in all of my attempts. I have at least that many, okay? So 10 successes or more, 10 failures or more, and then I can say, yes, it's going to be big enough where I can say, kind of thinking back, where I can say that the shape is normal enough that I'm going to approximate it with a binomial distribution. Okay? All right. So let's look at this example. Attitudes towards shopping. Sample surveys show that fewer people enjoy shopping than in the past. The survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed that I like buying new clothes, but shopping is often frustrating and time-consuming. Suppose that exactly 60% of all adult U.S. residents would say agree if asked the same question. Let X equal the number and the sample who agree. Estimate the probability that 1,520 or more of the sample agree. First, verify that this is a normal binomial random, first show that it is a binomial random variable. So binomial, check your bins. All right, success is agree, failure, don't agree. Independent, well, independent is that 10% rule. So I'm going to say the number that I have going on times 10 is 25,000. So is the population of U.S. adults bigger than this? Yes. So the population is greater than 25,000, so the 10% rule has been met. Is this a fixed amount, fixed number? Yes, it told us we're going to sample 2,500, so that's how many I'm going to do. And the probability, it told us, was always going to be 0.6 for success. Okay, so it just said suppose that exactly 60%. All right, so now we want to check the conditions for using a normal approximation. So now in order to use a normal approximation, I need to do my n times p, n times 1 minus p, and make sure they're both at least 10. So when I do n times p, I get out 1,500. When I do n times 1 minus p, I get out 1,000. So I have 1,500 successes, 1,000 failures, so I am above 10 on both of those, so yes, we may use the normal approximation. So now that we have shown all of this, we can calculate the probability of x greater than or equal to 1,520 using a normal approximation. So that would be a normal approximation, so a normal CDF. Start, just kind of a little recall, and mean, standard deviation. All right, so greater than or equal to 1,500, so I'm going to go 1,520 to infinity. But what's my mean and my standard deviation? We got to go find those. All right, so to find the mean, take n times p. So n times p would give me 1,500. To find the standard deviation, take n times p times 1 minus p, square root it all, and you get approximately 24.5. So go put that in your normal CDF, and you get approximately 0.207. So we can say the probability that we have 1,520 or more that agree is approximately 21%. All right, you try this one. See how you do. I'm going to go ahead and put up the answer, so if you need to pause me. All right, so the next thing we're going to discuss is a geometric setting. In a binomial setting, the number of trials n is fixed, and the binomial random variable x counts the number of successes. In other situations, the goal is to repeat chance behavior until a success occurs. This is a geometric setting, so you go until you get a success. It's not fixed. All right, so now it's a little bit different. We're still going to check binary, independent, but instead of a fixed number of trials, we go until we get the first success. And success is still the same. So this is the only guy that's different from a binomial. So geometric is that you're going until you get a first success. You do not have it fixed. Not fixed. Fixed is binomial. So here, this is bits, if you want to remember that. All right, so let's look at the example. Let y equal the number of attempts it takes to roll doubles one time. Each attempt is one trial of the chance process. Is this a geometric setting? Okay, so is it binary? Yes, we get doubles. No, we don't. Is it independent? Yep, rolling the die doesn't affect the next roll. So the trials, are there a fixed number of trials, or are we going until we get a success? So it says that we're going to keep rolling until we get doubles. So yes, it would be geometric there. Success, yep, the probability of success is always 1/6. So we are good. All right. So here, if you want to talk about the geometric distributions, okay? So just like the binomial, we only have the exact, so we could have 1, 2, 3. You can't get a 1.5. All right, so I'll let you read through these guys. You can pause me, and then we're going to keep moving on. We're going to do the birthday game. A random variable of interest in this game is that y equals the number of guesses it takes to correctly identify the birthday of one of your teacher's friends. What is the probability that the first student guesses correctly? What about the second? What about the third? What's the probability that the kth student guesses correctly? So, is this a geometric setting? So let's see. Success, get it right. Fail, get it wrong. Each guess is independent. We're counting the number of guesses up until we get it right. And on each trial, the probability of a correct guess is 1 out of 7. So the birthday, you could have Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. All right, so it wants to know what's the probability that the first person gets it right. So that'd be y equals 1. Probability of the second would be y equals 2, etc. So let's see if we get the probability of y equals 1 would just be 1 out of 7. The probability that it's 2 means, hey, the first person gets it wrong, and the second one gets it right. So there are 6 ways to get it wrong. All right, so then it says, oh, one person got it wrong, the next person got it wrong, the next person got it right. And you can keep going, and you can see the pattern going on here. That basically, you're going to have the probability of the number of trials minus 1. So that would be times the probability of the failure, or raised, the probability of the failure raised to the number of trials minus 1 times the probability of success here. Okay. If you like doing geometric in your calculator, which I like to as well, again, you're going to go to that second distribution and scroll down. Well, scroll up, I think is faster. And you're going to go to either the geometric PDF or CDF. Remember, PDF means just one value. CDF means you're accumulating for that value and everything smaller. The only difference in geometric is you don't have the n going on for the NPK like in binomial because you do not have a fixed number. So it's just PK. So you can just do your PKs. All right, can you tell I was a dancer? So you could find the mean of a geometric distribution. We've done that before. So here's one geometric distribution of the number of guesses required and what that would look like. So here you can see it's very skewed right. If you did the center of the mean, I wouldn't. I'd go ahead and find that median, okay? And you could put that into your calculator. It's just going to take a while. And the spread, you can find that as well. And you could do the standard deviation, but the IQR would be better when it's skewed. And here you can find, this is nice, the mean when you're talking about a geometric random variable is just 1 over p. So let's do an example. Suppose you roll a pair of fair 6-sided dice until you get doubles. T is the number of rolls it takes. So let's show that T is a geometric random variable. All right, binary, yes. Independent, yes. Trials, we're going until we get doubles. Success, always the same. Let's find that T equals 3. So here I'm just going to do a PDF, probability of success. So PK is 1/6, K is 1/3, or sorry, is 3. So I get about a 12% chance that I get exactly 3. It takes me exactly 3 rolls before I have gotten doubles. So I get doubles on my 3rd roll. So here's where it's fun. You can apply this to your games and go home and play with your parents and be like, oh, haha, I've got a strategy now in Monopoly. So in the game of Monopoly, a player can get out of jail free by rolling doubles within 3 turns. So what's the probability that this could happen? Well, now I'm going to do a CDF. Because I want the probability that I could roll on the 1st attempt, the 2nd attempt, or the 3rd attempt. So there's a 42% chance of rolling doubles in the first 3 turns. So is it more beneficial just to like go ahead and pay the money and get out? I'll let you decide. Okay, here is an AP question for you. I will let you work through this. I'm going to let you see how you do. And we are done with this section. Okay, A, it's not binomial because each child was not independent, okay? Because you sampled without replacement. All right, B, suppose that a group of 20 brontosaurs whose remains were found in the swamp had been made up of 10 males and 10 females. What's the probability that all 4 are going to be males? Okay, so all 4 males would be 10 out of 20, and then we took 1 away, so we're left with 19, and we've already taken 1 male, so we're down to 9. Taking out another male, so we're at 8. Again, taking out 1 from the total to be 18. Taking out another male, so you're at 7. Taking out 1 for the total, so you're at 17, and you can multiply across. So we didn't get to do binomial, geometric, or anything here because it was not a binomial setting. All right, C, the DNA testing revealed that all 4 femurs tested were from males. Based on this result and your answer from part B, do you think that males and females were equally represented in the group of 20 brontosaurs stuck in the swamp? Explain. All right, so here all males were, gosh, that was pretty low, 0.043. So females and males were equally represented. The probability of observing 4 males, that's pretty small. So if they were equally represented, you'd see a bigger probability. D, is it reasonable to generalize your conclusions in part C pertaining to the group of 20 brontosaurs to the population of all brontosaurs? Explain why or why not. It says no, we can't generalize to the population of all brontosaurs because it's not reasonable to regard this sample as a random sample from the population of all brontosaurs. There is a reason to suspect that this sampling method might cause bias. All right. So what we've learned about binomial settings, you can use this formula or you can use your binomial CDF as long as you're explaining everything. the mean and the standard deviation for binary, how to approximate normality using the n times p and the n times 1 minus p. So 10 successes, 10 failures. We've learned about geometric settings, the formula for a geometric setting, or you can use your calculator, and the mean of a geometric random variable. And then don't forget we learned about that 10% rule. I don't think it was on there, was it? Yeah, so don't forget about that 10% rule that we learned about. We're going to be using that a lot in modules to come. All right. See you in Module 7.